Okay, recap for what we have left when we go for a short our junior break. Okay, so previously we talked about galvanic corrosion. So um, and in galvanic corrosion basically is exchange of electron within two metals, right? So again, we have two brother here. If they meet together, and they are always, when two metal meet together, they will compete among themselves. They will look at their level. So in the corrosion, they call it nobility, right? Nobility. So if the level is higher, so this metal will call higher nobility. This one will become lower nobility. So those lower one, this lower one will become anode, and this lower one will send electron to the higher metals. This one become cathode, this one become anode. Okay, so as long as you understand this principle, you are okay for galvanic corrosion chapter. Okay, so as long as two metal meet together, they will compete among themselves, and then they will look for nobility. So whichever is higher, whichever lower. So those at the higher, how you know? I given you a table in your tutorial handouts already. So um, so if you look at the table that I give you, so there's a positive charge, negative charge, and all this. So the more positive it is, the higher nobility it is. So the higher one and lower one. So lower one become anode, higher one become cathode. And what happened to the anode? This one will always become the sacrifice metals, or we call it, this corrosion will happen at an anode, or those that have lower nobility. And when the corrosion happen, this one, the lower one, will contribute electron to the higher metals, right? So the higher metals basically is just lie there, enjoying his day and receive electron, right? So receive electron itself doesn't happen anything to the higher nobility, but the electron, where does electron go? Electron will always stick to the surface, will go to the surface of the cathode, higher nobility, and the electron will attract the positive charge around the higher nobility metals, or we call it cathode, right? So the positive charge will attract to all these negative charge here. Positive charge will attract, and positive charge, when they join with negative charge, what will they happen? They will become solid. They will become precipitation. They will become something that stick to the surface of cathode. Okay, so as long as you understand the principle, this principle uh, of Galvanic's reaction, then you are fine with the rest of the content in this chapter. Okay. Um, Previously we talked about a few parameters when we talk about Galvanic's corrosion. We talked about current. All right. So current. Macro cell current. Macro cell current means the total current you have in the cell. So previously we also watched a video, if you can remember. With the video, we have two metals and then link with the bridge. So each of the metals here, if you cut into half, we become half cell, half cell. Okay. So previously we cover all this current. All right. IM is this one, and not. IC is cathode, IA is anode. All right. So and then the surface of anode and cathode. M is anode, N is cathode. N is cathode. M is anode, N is cathode. So this is M, this is N. Right? M, N. Okay, so for this PowerPoint slides, as long as you see M and N metal, N always refer to the higher nobility. And we have a few calculation. All right, so these are all the important calculation. Okay, so if you want to find the corrosion rate, right? We have two type of I, small I. Again, small I, CORR, corrosion. This one is corrosion rate. This is a corrosion rate. Okay, CORR is corrosion rate. However, the small I, C, this one is cathodic current density. We have two different, although both of them they are look similar, but meaning is different. COR is the corrosion rate. IC is the density current for cathode, right? Cathodic current density. And then you need the ratio between the higher nobility metal surface and lower nobility surface, N divided by N, Sn divided by Sm. So this one we covered previously. Okay. Then previously we stopped at one graph, this one. All right. So previously when we talk about this one, we stopped at this chart. This chart is the reaction between zinc and platinum, between zinc and platinum. So in this case, if you look at the table that I give you, zinc and platinum, when they meet together, if you look at the table, zinc is below platinum. So, and zinc, the zinc value is below platinum. So in this case, when these two metals meet, they fight for nobility, and zinc is below platinum. So what happened? Zinc will sacrifice itself and contribute electron to platinum. Okay, basically platinum, again, it doesn't happen anything to platinum. Right, platinum just stay there and receive electron. And where does the electron go? It will go to the borders of platinum. And when the borders fill with the negative charge, what will it happen to the environment? All the positive charge around the platinums will attract to negative, right? So the positive charge will go and meet the E negative charge at the surface. And then when both positive charge, negative charge meet at the surface, they become stick together and become precipitation, right? So they will stay at the surface of positive this cathode here. Okay, so this is what happened. So when you're given two metals, the first step, you look at the table, compare the nobility. Then you draw two axes on your answer. One is E, which is the potential, right? E, and you draw the log I axis. These will be the two that you will see in the question. All right. So you just need to prepare the lines accordingly. So E and log I. You don't need to give the exact value in the axis over here, but you have to label clearly what they are. Okay. So if you're given two metals, they should be having two lines on the chart here. Right. So we're having a zinc and platinum. So those that sacrifice, right, below one, the chart will go up. Okay, you draw two lines, one line go up, one line go down. Okay, one line go up, one line go down. So those sacrifice one below one, you draw positive gradient from on the chart, and those receiving electron one, you draw negative gradient like that. Okay, why there is a one more line over here? Why there is one more line for the zinc? Because in this chart, we state one thing happened to the zinc. Okay, in the question, sometimes it was mentioned what happened to the lower nobility one. In this case, we mentioned zinc happened two process. It happened anodic and cathodic process. Okay, and the platinum only have cathodic process, right? So if you have Okay, if you have sacrifice itself, it will be positive gradient line. If you're receiving electron or Catholic process, then it will have negative gradient. However, for this case, because we have a setting saying that the zinc over here, all right, zinc is having two process. So it's having the anodic process and Catholic process. So you need to draw one more line for the zinc. Okay, that's why there's one more line over here. Okay, clear? Nan, you okay? Nan, are you okay?
Yes, sir.
Okay, okay, let me check the attendance again. Okay, Mohit is still not here. Okay, so when you start answering question, basically you should read carefully what happened to the lower nobility metal and higher nobility metals, right? So in this case, lower nobility metals having two process. That's why you're having going up and going down line. Okay. Once you are ready the graph with the correct line, then you need to start explaining some points, right? So first point the question will sure ask you to label what happened to before the coupling start, right? So point number one here is there is no corrosion happen, which is before coupling. So this is the first point, right? First point. So we pick the point where, if you look at the zinc graph, right? Zinc graph is going up and going down. You pick the intersection point where the Catholic and the Catholic and anodic process meet at one point. Means this point, the Catholic and the corrosion means that the corrosion doesn't happen. Not happen, but imbalance. So you can see at this point the two line collide means the process you can say as stagnant, means stop. There is no corrosion happen, right? So we pick this point. Point one is here, and then when after you pick one point, you draw a dash line, or you draw a very light line down, and then you label as I prime corrosion. Okay, I prime corrosion, COR. R prime corrosion means, again, I corrosion means corrosion rate. So I prime means before that thing happened. Okay, but in test or exam, normally I will just give you label A, label B, label C to represent something. So if this one, if the question asks you to represent, okay, point one to represent corrosion before coupling and label on the x-axis as A, then you label as A here. Okay, but this one is I prime corrosion, before corrosion. So before the two metal meet together. After you find the point number one already, after you meet point number one, okay, then the next steps, you go and find number two. Okay, number two here is when you join the two metal together. When you join the two metal together, or we say electrically connected. This is a definition for galvanic corrosion. When they are electronically connected, meaning the corrosion start happen already. Means when the electronic connected, means two metal meet together, they start competing already. They start the match, and they are nobility status matching. So those below one will contribute electron. So in this case, when the two metal meet together, point number two happen. So point number two, you just go to a little bit higher. You find one point a little bit higher to the platinum here, right? You go any place that higher than this point, higher than this point, then you pick number two. So number two, you use your ruler, again, make a dash line over here, and then you label this one as after coupling. This one is corrosion rate after coupling. Okay, so this is corrosion rate after coupling. And then after that, you stop here. Then you use your ruler to extend this line, this point, to the left of the graph. To the left of the graph, you will get one potential value. Again, y is your potential value. You expand to the y value, which is E sub corrosion. This is your potential corrosion. This is the voltage. When you measure the potential between two metals, this is the reading that you get on the voltmeter. Okay, so this will be the value on your voltmeter. Okay, so if the question states that there's a reading of, let's say there's a reading of 12 volt when the two couple join together, or when the voltmeter was used to measure the galvanic potential, then the line that you extend to here, this one will read 12 volt. 12 volt will be this point. Okay, once you find point number 2, point number 2 should be higher than this line. Any point that is higher than this line. Okay, so you pick point number 2, then you extend down, you get corrosion rate when you couple, and then you get potential when the two metal coupled. So same with point number 1. Point number 1 is before coupled, you get 1 E prime corrosion, means before you join the two metal together to the left. Okay, next we move at point number 3, right? So point 1 and 2 is basically on the zinc itself. Point 1 and 2 is on the zinc. So point number 3, what happened to platinum? Okay, platinum, they will share the same potential. Right, they will share the same potential. So it's just an intersection line of this voltage here from number 2. Okay, so when you reach number 3, okay, when you reach number 3, it means you look at what happened to platinum. So number 3 is a final condition where this is the cathodic current density. Where can you find the cathodic density for platinum? Okay, so this one is H2 platinum. Okay, this is the density current. This is density current for platinum. So again, still back to the higher nobility. So when you have a higher nobility, you will receive electron, and then this station we call cathodic process station, or this higher one. So this one, when you look at the higher nobility, one scientific term we use for cathodic station, we use current density. Okay, current density. Those lower level metals, or in this case zinc, we use corrosion rate. So I hope you can, by looking at the technical term itself, you can differentiate what is higher metals and lower metals, right? So if you see corrosion rate, means it's at a lower level. If you see density current, means it's at a higher level. Okay, so both are I, but they means different, right? They means differently. Okay, and you see the notation here, IH2 platinum. Why there's a H2 there? Why this line is there's a H2 reaction? Again, previously when we derive this graph, we have one condition set up. Where does these two metals put together? They are in an acidic solution. These two metals, they dip into acidic solution. And when you think of acidic solution, what do you think? You think of the pH value, right? So pH value, what does it mean? What does it mean when it becomes acid? What will happen when it becomes acidic? Alkalic. So when it becomes acidic, means lower than 7 to 0, right? So the more acid you go, what does it mean? It means you have more H positive. You have more H positive charge in the solution. right? The more H positive we have, the lower pH value you have. Okay, then what happened to alkalic? Why? What means by 7 and above, maybe up to 14? What does it mean? It means that in your solution you have more OH negative. You have more OH negative. If you have more OH negative, means pH value will be higher towards 14. Okay, so acidic solution means you have H positive. Okay, you have more H positive. It doesn't mean that you don't have OH negative. You still have OH negative, but the concentration of H positive is higher in acidic solution. That's why you get the pH value less than 7. I hope you have a clear mind of what is acidic. So when you put two metals together in the acidic, so there is a H positive charge on there. So in the solution, again, higher and lower, right? Higher and lower metal. When two metal meets together, what they do? They will fight. They will look for nobility. So in this case, zinc is lower nobility. So what does the lower nobility metals do? Again, sacrifice himself by donating electron to the positive, to the higher nobility metals here. And what happened to the higher nobility? Basically, nothing happened to positive or to the higher nobility metal. They just lie there and receive electron. And you should ask question, where does this electron go? They will go to the borders of the higher nobility metals here, or we call it cathode. So they will go to the borders. Then what does this negative charge will do? It will attract all the positive charge around the higher nobility. So in this case that we have, they are in the acidic solution. So what does acidic solution have? H positive charge. So H positive charge will attract to the surface and it will combine with E negative here. Okay, so that's why on the graph over here, you see on the negative gradient here, this line, there is a H negative there, and it is not platinum chemical reaction because platinum doesn't happen anything. So only chemical reaction that happen on the platinum is what happened at the border of the platinum. So in this case is H positive, right? What happened to H positive? H positive will combine with electron become hydrogen. Okay, that's why you see chemical reaction over here. So 2H positive plus 2 electron will become H hydrogen. That's why when you put platinum and zinc together, electron transfer, and then hydrogen charge will combine with E negative become hydrogen. Visually, you will see bubble come from the platinum side. Small bubble. What is this small bubble? From this equation is hydrogen gas. Okay. All right. So I hope you can understand what does this happen. Okay. Then zinc this side we already discussed in chapter 1. So zinc, it will sacrifice himself, donate electron. So when they donate electron, it will become charge. Z2 positive become plus 2E negative. Okay, so I hope you guys clear. First, look at the question. Second, look at the question, what is the material? After that, refer to a table, look for nobility, draw positive gradient, negative gradient, and then look carefully the question. Does the question really tell you what happened to the lower nobility? If the lower nobility have additional process, for example, in this case, you have two process on the zinc, right? You have cathodic and anodic process. So you need to draw one more line on the graph for cathodic process. Can all right. So just now we explained about point number 3. So point number 3 share the same potential from point 2 because once they coupled, you will measure the same voltage and then you expand down, you will get one I value here. I value here for higher nobility, it is not corrosion rate anymore. Higher nobility, we call it current density. and not corrosion rate. So in this here, you see IH2.pt is just a notation saying that it is the process, is a density current to generate hydrogen on platinum site. Okay, so this is number 2. Okay, I hope you can understand. Then you share the same voltage to point number 4. Okay, so again, point number 4, if you have point number 4, this one is Catholic process. What I mean by Catholic means is at a higher level process. So higher level process, when they expand down, the I component here is not corrosion rate. Higher level one, when you have a negative gradient line, when you expand down, it is not corrosion rate, but it's a density current. Okay, that's why you see I H2, Zn. This one it just represent the Catholic process happen at zinc station. Okay, and then the same process happen to hydrogen. Right, hydrogen will attract to zinc. Okay, so we have 1, 2, 3, 4 here. All right. Any question on doing or drawing the graph? Any lines that you're not sure?
So far, no, sir.
Good, yeah?
So far, no, sir.
Okay, good. All right. Okay, let me check the attendance again. Okay, Muti is still not in class. Okay, next, there's something special about the graph is the dotted line here. So what does this dotted line means? Dotted line represent the global equivalent Catholic curve. Okay, so it just tell you that this is the a condition. As you can see, this dotted line have the same gradient for all the Catholic process here. You can see the gradient of dotted line. Same parallel like the platinum and the zinc at the higher nobility. The gradients still same. So if you want to find the global Catholic curve, what do? You just copy, you just put your ruler parallel to this line, and then push your ruler a little bit ahead when touching this line. You draw the dashed line to represent as global Catholic curve. Okay, so it's very easy to find this line. It just, what you need to do is just you put your ruler on this line here, then you slowly push your ruler towards point 2, then you use your ruler to mark the dashed line, and this one become global Catholic curve. You know that all these are Catholic, right? So this one is a global Catholic curve for the zinc. Okay. Then the rest is just self-explainable. With this, as you can see, if you understand point 1, 2, 3, 4, it just means that this is point 1, right? This is point 1, point 2 after coupling. So after coupling, you can see that the corrosion rate after coupling, the corrosion rate for zinc, meaning again when we talk about corrosion rate, it means a lower level metals. It increased from this point to this point. From this point to this point. This in the graph, you know that when your graph is moving to the right, the higher value it is. So again, but this one is log I, but the value will increasing towards right. So your corrosion rate before coupling, after coupling, what happened to the corrosion rate? It increased from this point to this point. What happened to the voltage? What happened to the potential? Right. if you look at potential, before coupling, after coupling, the potential also increase from this point to this point. Okay, this one happened to lower nobility metals or anode. Okay. Okay, this one is about hydrogen revolution, meaning hydrogen revolution means you are generating hydrogen or you are combining electron with the positive charge. In this case, hydrogen was created. So as you can see here, what happened if you have the coupling happen? The potential is same. Potential from between the two body here, platinum and zinc here. So they share the same potential, but you move down. You know that this one is current density. So platinum current density will be higher than the zinc in this case. All right, all this you just read from the graph. Yeah, so this one you can see another explanation here. You can see what happened to the zinc itself, to the zinc. Zinc, you can change from 0.4 to 0.1. So quite interesting observation here. You see the 0.4, your potential is at this level. But 0.1, you know that 0.1 is before coupling. So the potential between 0.1 and 0.4 is this one. And then the density also change. Okay. If you understand this graph, then we're going to move faster when we move to this graph. Yeah. Yes. No. Okay. All right. So, okay. All right. So the next one, we look at another sample. So now we look at active passive metals, titanium and platinum. Okay. Titanium and platinum metals. So when you put titanium, platinum together again, what you do first? You look at the table that I give you, I think in tutorial, I forget which question already. There's one table that tell you how the potential chart. There's a potential chart. You look at the table and then you go and look for Ti, titanium, platinum, PT, and you look at the value. Whichever higher positive, they become higher noble, right? Or by looking at the table, you know the higher one is at the top one. So in this case, titanium and platinum, they meet together and they are at the deaerated acid solution. Deaerated means there is no oxygen inside there. Deaerated means you take out the oxygen. Acidic, again, acidic solution, you know, when you see acidic solution, you know what is the positive charge inside there already. Okay, so acidic solution gives you H positive, right? Okay, so again, same process. Two metals meet together, they will fight for nobility. So how do you know which one higher, lower? Refer table. So those lower one, what happened to lower one? They will experience corrosion. They will sacrifice themselves. When they sacrifice themselves, what they do? They donate electron to higher nobility. What does the higher nobility metal do? They doesn't do anything. They just lie there and join, receiving electron. And then what does the electron go? Go to the borders of your higher nobility metals. And then what does the after effect when the electron reach the border? They will attract the positive charge around the higher nobility. In this case, you're having acidic solution. So what does acidic solution have? H positive charge. Again, H positive charge will go to the borders, combine with E negative, become hydrogen. Okay, that also called hydrogen evolution. Okay, right. So if you look at this chart, you can see a few points there. All right. So E lock, and then you will see interesting behavior compared to the previous one. Here you see titanium. Titanium curve look like that. Okay, a bit different. So titanium graph look at that. In fact, you have this graph on your tutorial handouts already. So but it's very small, right? So you have this line for titanium, and then you have the you have the platinum. Okay, platinum is quite high nobility, so you always have the negative gradient when you compare to lower nobility. So you have two lines here, one is going up, one go down, but in this case you have a very spatial behavior for titanium. Yeah, this one. But at the beginning you see is starting positive gradient, but here you have some very weird observation, right? So you still prepare two line, and then in this case you see the titanium here also have one more line. It means that on the graph, if you see three lines, one of it, lower nobility one, will always have two process happen, anodic and cathodic process happen at the same time. All right, so you have two line for titanium and then the platinum. So I believe I did explain why there's a H positive plus 2E negative on the platinum, right? Because platinum is a higher nobility, we receive electron and just lie there and join itself. So hydrogen go and get the electron from at the border. Okay, so I did explain how to get this line. So you just basically just copy this gradient, move a little bit higher, and then you draw. Okay, so for titanium, you look at the titanium point number 1 before coupling. So before coupling, you find the intersection point between the cathodic and anodic process on the same material itself. So point 1, you get I prime corrosion, means corrosion rate before coupling, and E prime corrosion means potential before corrosion, point 1, and then you move up to point 2. Okay, point 1, move up to point 2. Okay, so point 2 is the global cathodic curve. So point 2 will move down, you get corrosion after coupling. Okay, you get corrosion after coupling, and then you extend to the left, you get corrosion potential. This is the corrosion. E corrosion means when the two metals meet together, that is the voltage that you can measure with the voltmeter. So this one, you get one value here, and you use a ruler just to extend to the y-axis with your potential. It will intersect with your platinum, which is a higher nobility metals, and the zinc itself. The titanium itself. So what is important for point 3, you expand down, you can find higher nobility, you can always find the density current, I, H2, PT, and the same value of potential. And when it intersect with the titanium itself, you get density current for titanium. Okay. The rest is like what I explained just now. The process system, that this graph, what is important on this graph is that you have seen what is the titanium and platinum graph before. Okay, the point number 2 for titanium is at passivity zone, and corrosion rate and so on drop to passivity current, at least one order of magnitude order. This is what happened to the titanium at point number 2 here. So point number 2, you can see that the I here drop to lower level, 1 to 2, but you expand down the value. 1 is here, 2 is here, again This line, lower nobility one, is represent corrosion rate. So actually corrosion rate drop on this, corrosion rate decrease on this graph. Corrosion rate on this graph is decreased. I prime is here, but after coupling, you see what happened? After coupling, the value is on the left of the chart. It is lesser value. It means the corrosion rate reduced. Okay, I hope you're able to read the graph. So from here, 0.1 to 0.2 means titanium itself, it dropped corrosion rate, means decrease corrosion rate on this type of coupling. Okay, corrosion rate can be increased and decreased. In this case, it's decreased. Okay. So in this case, what happened if you're seeing the corrosion rate decrease? This is what we want in the real scenario, because this is the protection effect. You want to reduce the corrosion rate. That is the one of the objectives when we do corrosion control. We want to control the corrosion rate not higher but lower, either maintain or become lesser value on the graph. Okay, so this behavior, 1 to 2, drop 1, the corrosion rate drop, it achieve protection effect, just for your info. Okay, so how do you quantify it? You just take the differences between here and here. Take this one minus this one. You get the protection effects. And then 3, 4, you have the hydrogen evolution, like what we see. And you should understand why and how hydrogen evolution happen. Okay, how you get H2 gases when at the higher nobility or cathode. So these are the two graphs that I think the same size as your tutorial, quite small, but you will explain the concept. All right. So in summary, we have discussed about two in summary. So when you do coupling with noble and less noble, so corrosion rate of the active less noble increase, meaning if you join two noble together, lower one, the one that sacrifice itself, you are seeing increase in corrosion rate because they will sacrifice themselves. So corrosion rate will increase and they donate electron to the higher nobility. Okay, this is the summary for the graph. Okay. Okay, so for this one, the titanium, you see there's a decrease. So it means that this, because it's a different metals, right? Those that have, in this case, you see titanium decrease. On the graph itself, it just tells you that you have a protection happen. Okay. Next, we look at, okay, I think we go for a short break. All right. Let me stop the recording.